In this video, we're going to look at the idea of equilibrium as it applies to a system of forces acting on an object. Okay. Now, so generally the idea of equilibrium is that one rate of change is balanced by another rate of change so that the net rate of change on the system is zero. In the case of forces, everything's going to sum. The net force on a system will be zero. So that system will be in equilibrium because all the forces are balanced. Okay. And the way to do that is to look at the force in each of the directions, sum them in each of the directions involved, and check that they all sum to zero. Otherwise, the system won't be in equilibrium because there'll be a net unbalanced force. If you're in 2 dimensions, then you have 2 directions to check. If you're in 3 dimensions, you're going to have 3 separate directions. So the number of directions in which to check will depend on the dimension. 2-dimensional system, 2 directions. 3-dimensional system, 3 dimensions. Higher dimensions, then however many dimensions there will be the number of directions you have to check. All right, coplanar forces. Well, coplanar means all lying on the same plane. Hence it's coplanar. Okay, so these are forces lying on the same plane. So in the example here in front of you is a 2-dimensional plane. Coplanar forces all act in the same plane. A system is in equilibrium when there are no unbalanced forces acting. Okay, so let's have a look at an example here. We've got the following forces are in equilibrium. So we have this force R to the right, this force S vertically up the page, and then we have some other forces over here, 10 newtons pulling to the top left there, and this 20 Newton force pulling down a little bit to the bottom left. Okay, well, we can't just talk about a little to the left and a little bit down and so on. We need to set up a coordinate system. So here we choose our coordinate system, the Cartesian one here. We're going to choose to the right as our I direction, that's to the right of the page, and then vertically up the page at 90 degrees with respect to the first. Okay, Cartesian coordinate system, I to the right as plus, J up as plus, and so anything to the left is negative. Any force acting downwards is in the negative direction. Okay, so let's start with the I direction first. All right, so we have R acting along the horizontal axis here in the direction of I, so we have plus R. Okay, the next force to consider is we have a component of this force. Okay, so we have a component here, that component, and we also have, later on we'll look at a vertical component. We also have here a component of this force acting this way. All right, now later we'll look in the vertical direction after, but okay. Now, how do we measure our angles? Well, we measure with respect to positive direction of the horizontal axis. Okay, in the Cartesian system, the positive direction of the x-axis, we measure anti-clockwise. So we go around here, 90 plus 40 is 130 degrees. So we're going to have 10 times cos 130 degrees, and that's this one here, 10 cos 130 degrees. Okay, now this is pointing in the negative direction, and what you find when you evaluate cos 130, you'll find that it is a negative value. It's really the same value as by the symmetry properties of cos 60 degrees, okay, which is this to the right, but then a minus sign put in it. By the symmetry properties, it's minus cos 60 degrees. But if you just leave it as cos 130, your calculator or software or whatever program will automatically produce a negative result there. So we don't have to put a minus in front of it. Even though it's pointing to the left there, cos 130 is a negative value. Okay, over here, same thing here. When we do cos 260 degrees, okay, we're going to get a value along here, like that, and that will be cos 260 degrees, and again, that will give you a negative value. That will take care of itself easily. Okay. That will become, so we don't need to write a minus there. So we write this statement out here. Okay, next line down is that we can take the 10 cos 130 on the other side, the 20 cos 260 on the other side to give us R, and again, cos 130 is negative times minus 10 is positive, cos 260 is negative times minus 20 makes a positive result, and we get 9.9 newtons to the right. So R is 9.9 newtons to the right. Now next we need to look at is we need to consider forces acting in the vertical direction. So we need plus S in in the S direction. This one will have a positive component, okay? All right, and that will be 10 sine 130 degrees. And this one here will be 20 sine 260 degrees. Okay, so we're going to have here plus S plus 10 sine 130 degrees. All right, that will turn out to be positive, so that's fine as is. Plus 20 sine 260 degrees. So sine 260 degrees will produce a negative result for us. So let's take these last two terms to the right. S equals minus 10 sine 130 degrees, minus 20 sine 260 degrees. And when we evaluate that, okay, we will find that we get 12.04 newtons. Okay, notice the answer is positive. The signs here take care of themselves, plus 12.04 newtons up the page. Okay, now finally, in equilibrium, we can write the statement, the sum I equals 1 to n of Fi. That's now each I represents, so F1, F2, F3, F4, up to Fn represents all the forces acting in the problem. Okay, the sum of all those forces must sum to 0 for equilibrium. Okay, so when we add up all these things here, we've solved S to ensure that this statement is equal to 0. We've solved for R to make sure that R plus all of this adds to 0. Okay, so what were the values of R and S that made this system made the net force on this system sum to 0? And we found R to be approximately 9.9 newtons, S approximately 12.04 newtons. That is the system in equilibrium. Everything must sum to 0.